Speed is distance, and every piece of data must travel. Inside the CPU, distance becomes the enemy. Caches step in as the silent accelerator. Tiny memory islands close to the core, always ready, always watching. They form the hidden hierarchy that makes modern speed possible. Welcome to caches and memory. The CPU is fast. Main memory is not. That gap defines modern computing. A CPU can run billions of instructions per second, but waiting for DRAM slows everything down. It's like a sprinter forced to stop every few steps. Caches fix this problem. They create a layered bridge of faster, smaller, and closer memory. Their job is simple: feed the CPU at the speed it demands. Think of memory as a pyramid, small and fast at the top, large and slow at the bottom. Registers sit at the peak. Below them is L1, tiny and lightning quick. Then L2, larger and a bit slower. Then L3, shared across cores and much bigger. Finally, at the base, DRAM, where most data lives. Each level is a trade-off between speed, size, cost, and performance. This hierarchy is the backbone of modern computing. L1 sits closest to the core. It is tiny but incredibly fast. It is split into an instruction cache and a data cache, so the CPU can fetch both at the same time. If the needed data is in L1, the CPU never waits. L1 is the sprinter of memory, fast, precise, and essential. L2 is larger than L1 and slightly slower, but it is still far faster than main memory. It acts as a buffer and a safety net. When L1 misses, L2 steps in. It holds recent and likely data, creating a perfect middle ground between speed and capacity. L3 is shared across all cores. It is much larger than L1 or L2, and slower because it serves many cores at once. Its job is to reduce traffic to main memory. It keeps frequently used data close to the CPU. Without L3, cores would constantly fight for access. With L3, they cooperate, share, and reuse. L3 becomes the quiet negotiator. The CPU looks for data. It finds either a hit or a miss. A hit is instant. A miss forces a search deeper into L2, L3, or main memory. Each step is slower than the one before. Hits are valuable. Misses are costly. Caches exist to maximize hits and minimize misses. Caches rely on patterns. Temporal locality means that if you use data once, you will likely use it again. Spatial locality means that if you use one piece of data, you will likely use the next piece too. These patterns shape cache design. They influence blocks, lines, and prefetchers. The CPU predicts what you will need based on locality. That is how caches stay useful. You've now seen the silent structures that feed the CPU. L1, L2, L3. Hits, misses, locality, and prediction. All working behind the scenes. All built to keep the CPU running at full speed. Next episode, out-of-order execution, the hidden intelligence that lets the CPU think ahead. The journey continues. Thanks for watching, and I'll see you in the next chapter of this digital adventure.